Angular momentum, I think your book uses L, capital L. It's equal I omega. It's totally analogous to linear momentum, P equals mv, right? Instead of P, which is momentum, we've got L, which is angular momentum. Instead of mass, we've got moment of inertia, because that's what responds to torques. Okay? Instead of V, we've got omega, angular velocity. Let's just consider mass m, distance r, and angular velocity omega. Okay? This mass might be riding on a beam. It might be doing anything, okay? It might be a mass circling the center mass of a two-planet system, okay? And in circular orbit. Okay. Then what's the angular momentum? Well, I equals mr squared. The angular momentum is mr squared omega. What's the direction of the angular momentum? Well, what's the direction of omega? It's not around the circle. Well, it kind of is, but that's not something we can express as a vector, and omega has to be expressed as a vector. Okay. The only two directions we could use to describe motion around a circle, it's not a bunch of arrows chasing themselves around the circle, because that's not just one vector. Okay. The only directions that could possibly be are perpendicular to the circle. There's no direction in the circle, in the plane of the circle, that matches the angular momentum. Okay, because there's just one angular momentum here. There's just one omega. If assuming this thing's moving at constant velocity, angular velocity. Okay, constant speed on the circle. Okay, so we make the convention that I'm going to use this definition. Here's the velocity. Let's let this r actually be the r vector from the origin out, or from the axis of rotation out to the mass. It actually be from any point we want to fix, but we don't want to get too far into that. Okay. So from the axis of rotation out to here, there's your r vector, there's your v. Okay. Your angular momentum is r cross v. I mean, sorry, angular velocity. Simple cross product. Okay. You know that in this case, V and R are perpendicular, right? Because V is tangent to the circle and R is radial. So tangent to the circle is perpendicular to the radial line from the center to that point. Okay. So there's our angular velocity. What's the direction of R cross V? If you have no like aerial calculus, don't say. Okay. Everybody else should know because chapter 1. Yeah. R cross V. Well, in this case, R is in this direction, V is in this direction. Ouch. There's the direction of your angular momentum or your angular velocity. Okay. What's the direction of your angular momentum? Well, it's just a scalar multiple of your angular velocity and mr squared is positive, you don't have negative masses, and r is just a distance. It's already positive, okay? And even if it was negative, the square would make it positive. So this is all positive, so L is just a positive multiple of omega. Angular momentum is just a positive multiple of your angular velocity. Okay. Now, let's say instead of a mass that's attached to whatever's rotating here, the analogy I used was we got one of these, which is very convenient because we can always have it in front of us. Ouch. I start saying bad words, but I think he's talking. Okay. So I'm saying, let's suppose that we've got this thing like here. And I take an airsoft gun and shoot an airsoft BB at this magnet. Well, it's going to bounce off the magnet. That's going to mess things up a little. Although we could analyze that if we know the coefficient of restitution. Probably even break the magnet. I probably wouldn't break this magnet. Okay. But if we got a little piece of styrofoam over here to trap the BB, okay, then that BB is going to have an angular momentum with respect to the system. Because just before the BB hits, it's just an infinitesimal distance away from being captured. Okay? So it might as well be moving in a circle. It's moving at 50 meters per second, coming in straight in this direction. It's going to have exactly the same effect on this system as it would if it was going around the circle at 50 meters per second. And all of a sudden got captured. Does that make sense? Because in both cases, it's moving in the same direction in the instant it's captured. Now, does that halfway make sense? It should, because that's kind of an important image. Well, that makes sense of the idea that the angular momentum of the BB when it's here is the same as it is here. Assuming it's not slowing down, okay? If I shoot at close range, it's not going to have time to slow down much. Okay. Well, if it's here, moving the velocity v, then what's its angular momentum? Turns out it doesn't make any difference whether it's here or back here 6 miles away. If it's moving on a path that takes it here, it's going to have the same effect ultimately as it would if it's moving around this circle and all of a sudden something reaches out and captures it. Okay. Well, let's figure out R cross V here. Let's call this R hat. Okay. I claim that R hat cross V is the same as R cross V. Why? Okay, now we've had some discussion. If this BB is captured at this point, it doesn't matter if it's been following a straight line or a curved line. At the instant of capture, as long as it's moving in this direction, the direction of this velocity vector v, it's going to have the same angular momentum. It's going to have the same effect on that rotational system. And I wish we could actually do that with an airsoft gun, but we're not allowed to fire airsoft guns. Okay. And it would be a hassle to set it up so we can do it safely. You can get injured. Hitching the eye can do that. Okay, so anyhow, okay, between this R and this V, you have a right angle. Now, what we're trying to establish is that omega, which I said here is R cross V. And we've calculated that because these are perpendicular. Just take the magnitude of R times the magnitude of V, and then the right-hand rule tells you the direction. Right? What is the BB's here? I'm saying it has the same angular momentum it will have when it's here relative to this axis. Because relative to this axis, its angular momentum is the R vector cross V. Well, you got to know the definition of cross product, and I emphasized why you really have to know that from now on. Okay? Multivariable calculus is a language of almost everything in engineering. Okay? The cross product is fundamental. It's fundamental here already. Okay, well, I'm going to use phi instead of theta, again, because theta's our angular position. Okay? Now here, well, in this position, it's magnitude of R, magnitude of B sine phi, but phi is pi over 2, which is just RV without the arrows. Now I should have had absolute value signs or norm signs with a kind of double absolute value. Okay. It's RV in the direction of R cross V. Now what's the direction of R cross V for R hat? Well, again, this cross with this, and if I straighten that thumb out, it's going to pop. So I'm not going to do it. You never realized that would be a handicap, some handwriting. I'm digging holes with a 20-pound digging bar. Doesn't bother my thumb. But handwriting, ridiculous. Okay. Established, it's RV here. Here it's not RV because R is much bigger. Okay, but what's R sine theta? R sine theta is just this big. Because, or R sine phi, because phi is here. R is the hypotenuse. Here's the opposite side. It's the same magnitude. Okay. So I'm going to say that magnitude of your R vector is equal to the magnitude of your R half vector times sine of phi. By this triangle, it's right there. As long as this line's in the same direction as this V, tangent to the circular path, there it is. Well, it's the magnitude of R hat, which is, magnitude of R hat cross V which is magnitude of r hat sine phi times v, which is a magnitude of r times the magnitude of v. It's r sine phi equals r, there it is. There it is in the picture sorted out, okay? Makes sense? Okay, so anywhere along this line, this thing has this angular velocity. And what's the moment of inertia? So what's the angular momentum of this thing? If it's moving, it's some angular velocity with magnitude omega. But let's say that this thing is moving with velocity v in this direction, and this one's moving with velocity v in this direction. And of course, v equals r omega without the arrow over it, times, I'm going to say times the k vector, assuming x, y coordinate system here, then z is in this direction. Okay, z is out of the board, so the k vector, unit vector in the z direction, multiply that by r omega, you have your velocity. Again, work that out if you don't understand it completely. Okay. And okay, that actually, that's probably confusing, because I'm confused two things in my own head. Forget that I wrote that. It's related, you'll see something like it in a minute, where v, the magnitude of these two velocities is r omega. Okay. Now, by what we just said over here, the angular velocity of this, my cross product symbol wasn't written very well. Okay. The r cross v for this magnet is in what direction? That's not magnet for this mass. Well, for this mass, we could use the r vector here. Call that r1. And then a vector back up. I don't know what I'm labeling this. I talk about drawing good pictures, and I'm not doing a good job of that. They'll call this vector R1. Then we have a vector here. which is R2. Okay. Now, what's the angular velocity of this mass with respect to this axis? It's R cross V, right? So the R crossed with the V gives you a vector in this direction. Okay. And then you have an R cross V for this one. All right. And here's your R and here's your V. Well, if you cross this R with this V, you still got to turn it to the right, and it's still going to give you a vector parallel to the vector you get here, because both are tending to rotate this thing in the same direction. So what I'm going to say is just apply this idea to this system, and you're going to see that the omega is the same for both of these, because the R cross V is the same. So that L we're going to say is L1 plus L2. The angular momentum of the whole system is the sum of the angular momentum of these two masses. So the angular momentum of mass M1 is going to be M1 R squared times omega plus M2 R squared times omega. The same reason that the angular momentum of this dB, wherever it is on that path at that velocity, is R cross V. And the momentum of this, just the same thing. It's R cross V, where R is this vector, but it's going to have magnitude R cross V equals omega, same omega for this one as for this one. And the angular momentum then is just going to be mR squared omega for each. Which is just your total moment of inertia, because you're just adding up your mR squareds times omega. Now, all this is just to emphasize that something doesn't have to be moving in the circle to have an angular velocity with respect to the axis. Okay. So if I no wonder that thing wasn't moving much. Had two magnets sitting here, and that was holding it pretty much in place. Okay. Now we see. And we're just kind of serendipitous multiple. Let this thing play out. Okay, anyhow, we can't see this on screen. Something just happened where I reached two magnets that messed up something else. Okay. Okay, so if this is free to rotate, then if I toss this magnet at the other magnet, let's make sure it's going to attract. Okay. then don't want to get too close. If I toss this nut at this magnet, it's going to cause a little bit of rotation. Okay. Now I don't have a good, my fingers don't make a good frictionless axle, but this thing would then start rotating. Now I can demonstrate that with the apparatus here. Go. That's actually going into something very much like a angular simple harmonic motion. It's going to start rotating back now. Okay. We could figure out how fast I toss that thing. Like I could do a similar toss at a horizontal here and see how far it goes. Projectile behavior would tell us how fast it's going. We could predict what the change in the angular momentum ought to be. And see if the system confirms it. Okay, probably do that on Friday. Because that's a simple, short thing we can just do. We just observe how far the thing displaces, do some torque measurements and so forth. Okay, well, there's that. Okay, so that's one of the big points I wanted to make about angular momentum that we didn't talk about last time. Okay, and again, it's a big deal. We've got a planet and an asteroid, say, passing by. Right? So that asteroid's moving at just the right speed in the right direction. It'll get captured and maybe even into a circular orbit, although that would be almost infinitely unlikely to get a perfect circular orbit out of an asteroid. Whatever that asteroid is doing, though the Earth is going to capture. So let's just assume that it does happen to be moving with a velocity that's perpendicular to the rate of velocity. In other words, a velocity would be tangent to the circle. Okay. Oh, now I'm going to try to draw a circle. That's even worse than usual. Okay. Anyhow, there's a circle. Imagine there's a circle. It needs a whole lot of cosmetic surgery. So that's so bad. I gotta draw it. You know, I'm sorry. Not sure anybody will be watching, but these videos are probably going to survive me. I don't want to go down in disc history or whatever it is. Okay. I'll have it over here moving in this direction. Okay. So we have your path. Just the right velocity. So that this little m here, this mass big M. So the little m times v squared over r, which is a centripetal acceleration, right? Just happens to be equal to the force for the gravitational attraction between these two masses. Does that make sense? Well, now all you need is a formula for the gravitational force between mass little m and mass big M, and you can solve for the speed in the orbit. Okay. Or if you like your speed, then you've got to figure out your radius, but that probably wouldn't be something you'd ever need to do. Okay. And remember, I posed a problem. If you got just the right speed at this radius, what speed are you going to need at twice that radius? Okay. We're thinking about, I think it's in that problem set, but if it isn't, it's going to be in the next one. I posed it last class, and I wrote something down ridiculous that it didn't work. And that was the end of class, and I didn't want to take time to sort it out. But you can write down an equation and figure out velocity you would need out here. Form another supernova. Another thing we talked about, and we're out of time, but if you have more velocity, say in this direction, then that's going to give you an elliptical orbit. Okay. And I'm not going to have to draw that because I'll do such a bad circle to start with. Enough velocity, and if you integrate the gravitational force from the surface of the planet to infinity, you get the potential energy relative to infinity. Okay. Or you get something equal and opposite to the potential energy relative to infinity. And you solve that for the velocity, and you get the escape velocity. And that seems that's related in a kind of a neat way to the velocity you need for a circular orbit. Okay. Okay. Remember what we talked about for that beam. Or equal K times theta. Implies simple harmonic motion. Now, the thing I asked you to do in the problem set for simple harmonic motion, I just gave you like that equation and told you, okay, confirm that every one of these formulas I give you is a solution. Every one of these formulas I give you for the position as a function of time is a solution. Okay? That's really easy. All you got to do is just invoke derivative of sine with a little bit of chain rule. And you confirm it, but you want to get used to that. Okay? And you want to get used to it now because we're going to build on it. And do some observations in lab that build into what we're talking about with all three of these things. Okay? And then we spend we'll only have 2 weeks of class left as of the first of next week. One before Thanksgiving, one after Thanksgiving. Of course, we do have a class on Monday, so I guess we have 2 in the third weeks. Okay. I usually don't give an assignment over Thanksgiving, but you got the ongoing project of catching up, and you're probably going to need to spend some time. Hopefully, we'll be caught up, be able to enjoy the whole Thanksgiving break. Okay, because it would be good for your mental health coming into finals. Never worked out that way for me. Okay, or anybody I ever knew, but hopefully it will for some of you. Okay, anyhow, good. I'll see you Friday. And we'll continue on with all this.